PhD in chemistry from Queen's University and a Bachelor in Physics from the University of New Brunswick. Today I'm going to run through a few undergraduate level physics questions. So here's our first one. What is the relation between angular velocity and linear velocity? So this would be, I'm going to test how well I can draw a circle here, but this would be referring to in circular motion. We have some radius for the circle, and the linear velocity was actually kind of perpendicular to that circle, but the linear velocity would be perpendicular to this radial line, whereas the angular velocity, the angular velocity would also be perpendicular, but it runs around the circle. And so the way that this expression is derived is by considering similar triangles. And so if we consider a small wedge of angle d theta, then each of the arms is r. And so this is our dx down here, or up here, sorry. And we can rationalize what that's going to be based on sine laws, actually. So if we call this angle up here phi, then we would say that r over sine phi is equal to dx over sine d theta, or dx is r sine d theta over sine phi. Now if we remember, inside a triangle phi, so if we consider this to be it's a triangle with both sides are r, so both these angles are the same up here, so those two angles are the same, so they both have to be phi, which means that our angle identity is 2 phi plus d theta equals 180. And so now if we take the limit as d theta goes to 0, then phi goes to 90. So then in our dx expression, as d theta goes to 0, as d theta goes to 0, sine d theta goes to d theta, and as phi goes to 90, sine phi goes to 1. 90 degrees, obviously. So I'll keep degrees on all these. And so then that means that as d theta goes to 0, our dx goes to r, say one thing and write a d, okay, r d theta. All right, so that means that that in there is r d theta. So if our dx, if we recall, v, our speed, is just dx over t, dx by dt, which is r d theta by dt, but d theta by dt is omega, so r omega. So then that is our relation between our speed and our angular speed. V is our omega. And okay, so then in the solution here, yep, and then so V is our omega, and then they also gave it in when the angular velocity is in RPM. So yeah, so this is in either degrees per second or rads per second. But when it's in revolutions per minute, you need to consider that a revolution is 2 pi radians, and a minute is 60 seconds. So solution is correct. I just added a couple extra little things. Okay, a particle in a uniform circular motion requires a net force acting in what direction? Okay, so again, just to rationalize through this, I'm going to attempt at drawing a rudimentary circle here, and we're going to pretend that it's a perfect circle. So there's our R line, there's one of our velocities, which is tangent to this R, and I'm just going to draw another one, and draw another one. And each of these we're going to pretend is tangent to this R. Okay. So we have that V is R omega, and so A, our acceleration, so this is our velocity perpendicular to the R. So our acceleration perpendicular is dv by dt, which is r d omega by dt. And so if we're in uniform circular motion, then our omega is constant, so this will be 0. So that means that if our acceleration perpendicular is 0, that means that our force perpendicular is 0. Right, as F equals ma. So if the force perpendicular is 0, that just means the force can't possibly act in any direction perpendicular. So it has to act, the force must be parallel to R. So in these cases I'm talking about perpendicular and parallel to our R vector. Okay? So the force is never acting perpendicular to R, it's actually acting parallel to R. And if we look at our velocity vectors, so this is without any real math, but if we look at our velocity vectors, they're moving inwards towards the circle each time, right? They're not going outwards, they're going inwards. So that means that our force, which is parallel to R, must act in along R towards the center. And so it's often called a centripetal force or a center-seeking force. Now let's look at the solution here. So an object in a circular motion, and I'll just put towards center, just to drive it home. An object in a circular motion is kept by a force called centripetal force. Centripetal force always acts perpendicular to the motion of the object. Yeah, so perpendicular to the motion is perpendicular to R, so it always acts parallel to R, which is towards the center of the circular orbit. Satellites have, yeah, okay. So, solution is correct. Looks good. And let's do this. Okay. So here I've got another rotational question. So a potter's wheel rotates with an angular acceleration where t is the time in seconds, a and b are constants, and alpha has units of radians per second squared. So if that's in seconds, then this guy here must be in rads per second to the fifth, and this guy here must be in rads per second to the fourth. I will point out that rad is not an actual unit, and so the way that I'll write these from now on is just 1 over seconds to the fifth and 1 over seconds to the fourth, giving alpha in 1 over seconds squared. And then it wants to get, and the initial position of the wheel is, we have a theta naught and an omega naught, and it wants the expression for omega as a function of t and theta as a function of t. The nice thing about rotational motion is it's very similar to linear motion. So that means that alpha is d omega by dt, and theta is and omega, there we go. Omega is d theta by dt. Obviously we have to go backwards because we have alpha, so that means that omega is alpha dt, or I guess the better way for me to write this is to say that omega is the integral of d omega, which is the integral of alpha dt. Okay. And I'll just leave that. So now if we integrate our alpha, we're going to integrate it from 0 to t. And when we integrate our d omega, we're going to integrate it from omega naught to omega of t. So then our alpha integral is just the integral from 0 to t of 4a t cubed minus 3b t squared dt. I'm just going to migrate this. Let me migrate a little more. Okay. And so 4 and a are constants, so they can come out front. And since this is a sum, we can split it up. So integral 0 to t of t cubed dt minus 3b integral t squared dt. And the power rule is you add 1 to the power and then divide by it. So it'll be 4a times t to the fourth over 4 from 0 to t minus 3b t cubed over 3 from 0 to t. And so this will be t at the top and 0 at the bottom. So the whole thing will come out to be 0 when it's 0. So that makes this 4a t, might as well cancel the 4's in retrospect and the 3's. while I'm at it. This will be a t to the fourth minus b t cubed. Okay, and a little bit more migration. So our d omega integral is a simple one, as the integral of d omega is just omega evaluated between omega naught and omega t, which is then just omega t minus omega naught. And that means that our omega of t is a t to the fourth minus b t cubed plus omega naught. Right, by bringing together our two pieces here. Right, so this integral and this integral, where that's the solution to the alpha integral, and I've just rearranged this solution from the omega integral. Okay, so there's our omega expression. And now I'm just going to erase everything. Actually, well, I'm going to erase most of it. I'm going to leave my omega expression. Should have been maybe a little bit more careful. Okay, so leaving my omega expression there. I might migrate it. So, and now starting off, so again, omega is d theta by dt. So that means that our theta is the integral of, I just realized that this is a bad migration, so I'm going to go down here a little bit. Theta is the integral of d theta from theta naught to theta t. That's going to equal the integral from 0 to t of omega dt. And we have our omega expression, and I'm just going to skip a bit of steps here and recognize that that's just going to be theta t minus theta naught, and then that's going to equal my integral from 0 to t of a t to the fourth minus b t cubed plus omega naught dt. This integral again is now a sum of pieces, so they can all be split, and the constants can be brought out front. So that's going to be a integral 0 to t to the fourth dt minus b integral t cubed dt from 0 to t plus omega naught integral dt from 0 to t. Again, these are powers, so you can just use the integration power law. So put them up by 1 and divide. So then this is a t to the fifth over 5 from 0 to t minus b t to the fourth over 4, 0 to t, plus omega naught t, 0 to t, and a little bit of migration again. Now, just as before, t will be t at the top end and 0 at the lower end, so it'll just be the whole expression will be 0, and it's the same for all three. So then this is just a t to the fifth over 5 minus b t to the fourth over 4 plus omega naught t. And then rearranging for our theta t, theta t is just a t to the 5th over 5 minus b t to the 4th over 4 plus omega naught t plus theta naught. Okay, so then there's our expression for theta t. And I'm actually just going to erase much of this. And see if I can't grab nope, failed. So that's our omega t expression. So looking through here, again, so the solution here has, you integrate, everything looks correct, and we've got the same expression. The powers of t here look to have done something rather funny. Yeah, so whoever submitted this solution had a t cubed instead of a t squared. I will point out as well that, as I showed in the beginning, the a constant was 1 over t to the 5th, 1 over seconds to the 5th, and the b constant was 1 over seconds to the 4th. And so if we multiply that by seconds to the 4th, so we multiply a by seconds to the 4th, then the whole thing will be 1 over seconds. And here again, 1 over seconds, which is good because omega naught will be 1 over seconds. And so omega t is 1 over seconds, as it should be. So it looks like a little mistake here on the t. And then if we move to our theta expression, again, correctly recognize that it's the integral. Luckily, that error from the first question was fixed here because it's a t cubed. But they incorrectly did the omega integral, so it should be, and then they're missing their theta naught. So, but the integration, at least on the t part, looks okay, but they're missing the t on their omega naught, and it should have had a theta naught. So this really just shows how easy it is to make small errors, and it's best to be careful and to watch what you're doing. Again, I'm going to point out that that's 1 over t to the 5th times, or 1 over seconds to the 5th, that's seconds to the 5th, so the whole thing's going to cancel, leaving you unitless. Again, here will be 1 over seconds to the 4th times second to the 4th, which is going to cancel, leaving you unitless. And that's 1 over seconds and seconds, again unitless, and your thetas are always going to be unitless. So that looks good from a unit analysis. And so I'd say the solution is small errors throughout. I don't know whether to say it's necessarily incorrect, but I'm going to do it anyway. Okay, and now, what is the moment of inertia of a disk? So, moment of inertia depends on how you define your moment. So, now the simplest is to have the moment be perpendicular to the disk, going through the center of the disk, And so the disk is spinning about that moment. And so that's the easiest moment of inertia to calculate. So for discrete masses, oops, I don't even know what that is. It's the sum over all your masses times the distance from those from your z here, or your moment, squared. But for a continuous mass, such as this disk, then we're going to use the integral like this. So you integrate over the entire mass, multiplying by the square of the distance from your moment. To solve this, we need to know what our mass is. So assuming again that it's evenly distributed across the entire mass, then the total mass is going to be the density, or the area density, I should say, times the area, right? Or the area density will be the mass over the area, okay? And the area of a disk is pi r squared, where r is the radius of the disk. Okay, so now to solve for our moment of inertia, we need to identify a piece of the disk that we're going to be integrating over, or our form of integration here. So if we consider a small ring at some distance r from the center, and the width of this ring is dr, then and the easiest way to visualize this is not actually to look at the ring, but to extend the ring out. And so the width of the ring is dr. And what's the length of the ring? Well, the length is just the circumference of a circle at a radius r. So that'll be 2 pi r. So that means the area of this ring, dA I'm going to call it, this small area, is 2 pi r dr. And now we can convert this small dA to a dm using our density, right? So dm is just sigma dA, which is then 2 pi r sigma dr. So there is our mass element that we're going to be integrating over. I'm just going to migrate that up. Okay, so putting this back into our moment of inertia expression, we now integrate, and our integral now is going to be over r, so it's going to be from 0 to r, the complete disk. And that'll be just r squared times our dm, which is 2 pi r sigma dr. 2 pi and sigma are just constants, so they can come out front, and the r will give us a 2 pi sigma integral 0 to r cubed dr. So the integral of r cubed, we can just use the power rule, so that the 3 goes up to a 4, and then we divide by 4. and so that's 2 pi sigma r to the 4th over 4 from 0 to r. And at 0, r is going to be 0, so the whole expression will be 0. So then our moment of inertia is 2 pi sigma r to the 4th over 4, or canceling the 2. Or canceling the 2, pi sigma r to the 4th over 2. Now we can clean this up a little bit because from before we have that our area is pi r squared and our mass is sigma times our area. And we can see here that pi r squared is in here, leaving an r squared, and we still have that sigma lying around. So sigma pi r squared is our mass. And so using those two expressions, we have that our moment of inertia is mr squared over 2. And this is neat because these are just parameters for the disk, right? So this is the total mass for the disk, that is the radius of the disk, and it's just divided by 2. Slightly more difficult, and remember this is the moment of inertia for a disk which rotates about a moment which is perpendicular to the disk, so you're spinning the disk. Considerably more difficult would be to compute the moment of the disk along a moment arm that goes this way. So now to do that, we would have to consider elements this way, because the r is always the perpendicular distance, right? So that's our r. And so then the question is, how does this length change with r, right? Because we need to calculate r squared dm. And the best way for us to get what our dm is in terms of our r is through our area expression. So we need to find some dA, and our dA in this case, again, our best chance at it is to have these length of our expressions multiplied by dr, because each one of these little things has a width of dr. And we can do this using just some geometry. And so if we look at one particular one, and we consider this to be a straight line, a distance r from the center, then that and that is definitely r, which means that this length is r cos theta, where theta is this angle in here. And now I've kind of switched to a theta, but it turns out that trying to calculate this in terms of r actually becomes quite difficult. And so switching to theta makes things a bit nicer. And our relation for our r here now is that r is, so this is the hypotenuse of our right-angled triangle, which I've drawn here. R squared minus r squared cos squared theta, or r equals r square root of 1 minus cos squared theta, which means it's r sine theta, which, I mean, we could have figured out anyway. So using that for our r, and using our length now, so now we just need to, I've got two d's there that I didn't notice before. Using that for our r, using our length as 2r cos theta, representing our, and now we need to turn our dr into a d theta. So dr is r cos theta d theta, just by taking the derivative of this expression. Okay, and there's our r, as there's two of them, or there's our length, as there's two of them. That means that our dA expression is now 2r squared cos squared theta d theta. And that means then that our dm is still just sigma dA. So we just multiply this expression by sigma. And now we're finally in a place to start our integral. I equals integral r squared dm, where now we just move everything over. So this is going to be, our r is just r sine theta, so there's going to be r to the fourth. I'll just keep the integral there. Sine squared theta. Actually, I might as well just do everything explicitly. So r squared sine squared theta for the r squared, and then our dm is sigma times 2r squared cos squared theta d theta. And our d theta integral is going to go from 0 to pi over 2. Right, so 0 would be it pointing along the arm, and then it pointing along this arm, and then pi over 2 would be straight up. And remember, I've already doubled the length. And the only other thing to consider here is that only covers half the circle, so our moment of inertia will actually be twice this, because we need to consider the other half of the circle. So we need to double the whole thing. And then continuing this forward. So I'm just going to clean up things a little bit. So pull the constants out of this expression. So there's a sigma, a 2, which I multiply by the other 2. So those 2's, the sigma, and then the r squareds can come out. So that's r to the fourth. And then it's an integral from 0 to pi over 2 of sine squared theta cos squared theta d theta. And that should be pi over 2. This integral is not easy to solve, so I ended up just looking this up. So most integrators or most integral tables of integrals will have this. And so then this is 4 sigma r to the fourth. And the indefinite integral here is 1 over 32 4 theta minus sine of 4 theta from 0 to pi over 2. And now if we look at this expression, we can simplify without really writing out or doing too much math here. So 4 times pi over 2 is 2 pi. So sine of 2 pi is 0. Also at the other end, sine of 0 is 0. So that means this quantity here is going to be 0 at both limits, so we don't even need to worry about it. And theta, when theta is pi over 2, this will have an actual value, but when theta is 0, that is going to be 0 as well. So that means this end of the expression we don't really need to think of either. So then all that's left is the pi over 2. So that means the whole thing is 4 sigma r to the 4th times 1 over 32 times 4 times pi over 2. And now we can start to pull some things out. So 4 times 4 is 16, 32 times 2 is 64. I'm just going to migrate. (16 over 64 sigma r to the 4th), and then that's just a quarter. So it's sigma r to the 4th over 4. And again, from before, our entire mass is pi r squared, and I dropped a pi, so there should be a pi in there and a pi in there. Right, so there's that pi I dropped. Pi r squared sigma. So there's our sigma pi r squared, and so then our moment of inertia is m r squared over 4. And so again, so now in this case, this is the moment of inertia for a disk rotating about a moment arm that lies through its center. So just to wrap things up, right? So we had a disk with the moment arm running through the middle and along one of the diameters of the disk, and the I was mr squared over 4. And then we also considered a disk where the moment arm was perpendicular to the disk and running perpendicular to the radial line, and that was mr squared over 2. Okay, so depending on how you set up your moment arm, you're going to get a different moment of inertia. Okay, so then if we look at the solution here, most likely, so it's just the integral, and quite a bit of the math is gone through here. And so this is for only for this case, but that's fine. It wasn't specified in the question. So I just added a couple extra things. So it looks good. Okay, so now on which of the following does the moment of inertia of an object depend? If I click that link, I don't believe it'll go very well. So we're just going to go through what the moment of inertia does depend on, and look at it that way. So the moment of inertia is for a discrete object, a sum over all the objects times the mass of the object and the distance of the object from the moment squared, or in a continuous object, the integral dm. And so what the moment of inertia depends on is the mass of the object and where everything's sitting, so how it's distributed, but it also depends on where the moment arm is chosen. So if in a disk, the moment arm or the moment of inertia for a moment which lies perpendicular to the disk and goes through the center of the disk is mr squared over 2, where m is the mass of the disk and r is the radius of the disk, while for a disk where the moment arm goes through the center of the disk and along the radius of the disk, the moment of inertia is mr squared over 4. So it depends on its mass, how the body is distributed from r, and also where you choose your moment arm. So if we look at the solutions here, so right at the bottom here, it says the moment of inertia depends on the total mass, shape, and density of the object, and the location of the axis of rotation. So that's what we went through here. So it doesn't depend on linear speed is shown here, or any other parameters. So that looks good. Solution is correct. All right. Okay, so a neon lamp. Neon is an element in the periodic table. So it's a pure element. That means that a neon lamp is going to be, and for the most part, actually no visible spectra are going to be continuous. The appearance of continuity is just the lines being really close together. But in any case, if we run through each of these anyway, neon lies in the visible spectrum. That's the reason why we see. That's why we see it, and also you can't have an infrared visible spectrum. Those are just two different areas of the electromagnetic spectrum. All right, so we have IR, visible, UV, and then obviously tons over here and tons over here. But in any case, IR and visible are two regions of the spectrum. And black body radiation is more is kind of deeper down here as well, but it's mostly due to temperature. So not a visible spectrum. So discrete would be the only possible answer. If we look at this closer to, so neon is a noble gas. Its electron configuration is 1s2, 2s2, 2p6. And a neon lamp uses electricity to excite this to several, what am I doing? Excited states. One of which could be this, which then relaxes back to the ground state, releasing light. All right, so that's what gives rise to the light, and it's from discrete energy jumps, or very well-defined energy jumps. So that energy for the photon, and therefore its frequency, is going to be determined by the gap in energy here. So it's going to be at a very well-defined single frequency, and so it's going to be a discrete spectrum. And yeah, answer is discrete, so that looks good. So solution is correct. Okay, and okay, so for helium atoms, what is the RMS speed at 295 Kelvin? So our RMS speed just comes from our relation that our average kinetic energy is 3/2 RT, But our average kinetic energy is, at least for a collection of similar masses, 1/2 mv squared, or where v here is our average speed, or our RMS speed. And so we can solve for our speed by rearranging this. These 2's will cancel, and 3RT over m square root. Okay. So we have our temperature. This is our gas constant, which is 8.314 joules per mole Kelvin. I believe that's right. Yeah. Okay. That's our temperature given in the question as 295 Kelvin. And this is our mass of a helium atom. So our mass for a helium atom is our molar mass, which is 4.002902 grams per mole. But we need the mass of an atom, so that means that mass is our molar mass divided by our Avogadro's number, which is 1/6.022 times 10 to the 23. So that's 1 mole, and that's atoms. And so doing that multiplication, grams per mole, 1/6.022 times 10 to the 23 mole. So the moles cancel, and we get got carried away there. Since that's already in joules per mole Kelvin, we actually don't need to remove the mole. That's my mistake here. All right. But what we do need is, because joules are kilograms meters squared per second squared, we do need this in kilograms. So we need to use multiply by 1 kilogram per 1,000 grams. So the grams cancel. And then this is 4.002902 times 10 to the minus 3 kilograms per mole. Okay. And so using that mass and the other expressions, our RMS speed becomes square root 3, 8.314 kilograms meters squared per second squared mole Kelvin. T is 295 Kelvin. So our kelvins cancel, and divided by our mass, which is 4.002902 times 10 to the minus 3 kilograms per mole. And extending that down into kind of a funny shaped square root. Kilograms cancel, moles cancel, so leaving us with meters squared per second squared, which when we square root will be meters per second, which is what we want, because that'll be a speed. So then our average speed, running this all through a calculator, square root of 1.838138 times 10 to the 6 meters squared per second squared, or our average speed is 1.36 times 10 to the 3 meters per second, just rounding at the very end. And if we go through the solution here, so again, so using everything in kilograms, putting everything through, doing the math, so 1355, so rounded to 1.36, and so that looks good. Okay, and so we're asked to rank the following electromagnetic waves on the basis of speed, frequency, and wavelength. So we've got green light, infrared light, FM, AM, X-ray, and yellow light. So as far as speed goes, all electromagnetic waves travel at the speed of light, or in a medium, it'll be C over N, where N is our index of refraction. So all these electromagnetic waves all travel at the same speed. Frequency, our electromagnetic spectrum is, so AM radio is our lowest. AM radio is our lowest, FM radio is the next, IR, and then yellow, green, and then X-ray, because X-ray is way out. So in terms of frequency, the ordering would be like this, right? So AM is our lowest frequency, followed by FM, followed by IR. Yellow is lower frequency than green, and X-ray is way up at the top. Recall that energy is h nu, so it's proportional to frequency. So this ordering also follows what you'd expect from the energy. And then lambda, so V is nu lambda, or lambda is V over nu. As they're all at the same speed, it's just an inverse relationship to our frequency. So that means our wavelength will be the opposite. Okay, and now checking the solution. Radio, okay, so AM, FM, IR, yellow, green, X-ray, and then it goes the opposite direction for wavelength. Okay, looks good. Solution is correct. And looks good. And I'm gonna actually just stop it there. And say that's my time for today. So those are gonna be all the questions I'm gonna go through with that one. Thank you for listening. If you enjoyed this, please subscribe to the OneClass channel. If you'd like to add questions, please submit them there. This has been Jeff Krause from OneClass, and I hope to see you again.